Welcome to the third part of the lecture. We'll be looking into the dimension examples here. We need to talk about applications. So applications, these are basically the equipment that we are driving. Application can be a pump, wind turbine, compressor, elevator, electric car, flying apparatus, drone, aircraft, whatever. So application is where we apply our system. Our system, I will remind you, it's a motor, gearbox, frequency converter, transformer. That's maximum what we can put together in DriveConstructor. And application is everything that we can drive, set in motion with our system, or take energy from the motion of this mechanism. So applications are often divided or classified according to the torque or power that they exhibit across the speed range. So what, for example, means having square torque? That means if we have torque on the vertical axis here and speed RPM on the horizontal, then square torque will look like that. Okay. So it's not linear, it's quadratic. So torque will be proportional to square of n, square of speed. Constant torque will be different. It will look like that. So torque is constant. Of course, for each torque type or torque curve type, we can find many applications. For example, for square torque, it's first of all pumps, fans, and mixers. For constant torque, there will be different class of applications. So it's all kind of conveyors, roller tables, elevators, screws, compressors, extruders, kilns, and many other applications. And for each of these kinds of applications or groups of applications, there are a little bit different things which we should look at. So you see, for the square torque, this is one set of things we need to check, and for constant torque, that's another set of things. When we will be talking about constant power, then we need to draw it again. So our axis, speed, power, and constant power is looking like that, constant. What is happening to the torque then? Because we remember the power is the product of the torque and the speed. So then our torque should look like that. So this will be torque. Torque, and this is power on the same axis. And again, you see that there are different applications which show the same character of power across the speed range. And then we have different things to check working with these applications. We haven't talked about transformers yet, so maybe it's time to mention them. So first criteria for choosing the right transformer is, of course, the voltage rating of this transformer. So what is the highest voltage it can work with, and what is the lowest voltage it can transform the high voltage into. So what is the ratio? And it should have the apparent power which is higher than certain number. So of course we start with motor shaft power here, so you find it in this formula, and then apparent power of the transformer should be higher than this motor power with the range or the set of coefficients, a description you find here. And also again recommend you to go and read books from AB or Danfoss on this topic, so they explain it very well. Let's look into a couple of examples. So example number one is a pump. You can see it here on the picture. So this is the pump, and here's the electric motor and driving this pump. And this is obviously the pipeline with some liquid. Pumps, as we remember, they have quadratic torque. So torque looks like that. This is speed and this is torque. And in this example, our pump runs up to 2000 RPM, and its power consumption at this RPM will be 15 kilowatt. And we have given the network. So this is the network at this particular plant or factory or wherever we have the pump. So we see immediately that 2000 RPM is not very convenient RPM, because usually our motors are either for 1500 RPM or for 3000. So let's see what we get. Before we look at the charts, we need to talk about the inverter selection. So there are some expressions which are quite complex and not very practical to use in most of the cases, but they exist, and at some point you may need to look into them if you really professionally work with selection of the components for the drivetrains. But to simplify everything, we can limit our level of depth here to the simple equations. Or inverter current should be calculated from the motor current, motor rated current here, IN, as well as load torque and rated torque of the motor. But this formula will be valid below field weakening point. That means it is to the left from our rated point. That's this way. So you remember, field weakening point is the point after which our flux gets weaker than before. So before it was like that. So when we are above the field weakening point, we use another formula, which is also not very complex. And our inverter current then should be the one which is higher, this one or the one from the previous slide, IM. This is the dimensioning criteria for our inverter. So now we see the chart, which may look from the first glance a little bit too complicated, but I will explain what is here. So if we try to choose or to use two-pole motor, 3000 RPM motor for driving our pump, then we are here on this line. So 2000 RPM will be somewhere here, and this is where we put the operational point of our pump. So our system should then have the torque not lower, at least than this point. Okay, so this is the system curve, like a generic system curve here. So you see it's 100% of torque here. Now, if we like to use 4-pole motor, so we are there, and for the 4-pole motor, 2000 RPM is here, and this is exactly where our pump is. So this is the same pump, the same curve basically, but depending on the motor choice, we find it here or we find it there. So both cases are valid. So in both cases, it will be the right choice. But now we see, for example, that in the first case, case number 1 here, our pump, where its torque is quite close to the rated torque of this motor. So it's maybe 5% difference. While in this, the second case, case number 2, we have quite a gap between like the loadability of the system and our pump here. So it looks like pump or case number 1 with 2-pole motor looks a little bit more advantageous, but this is really something that you need to calculate. I'm not sure that you will be trying calculating it now, but you can do this exercise. Check again ABB guide for dimensioning systems. You will find a good explanation of this example there. Okay, in both cases, what is important is that our system curve should be above these points were above the generic system curve. See, there should be some buffer between, maybe ideally as small as possible, maybe 2%, because the pumps, they don't have any overloads, so you can dimension it very close to what you really need. But if you have 5–10% buffer above, that would be good dimensioning, no problem. I know I'm going very quickly through these examples, not explaining much, but this is only because I want to give you a very brief introduction into how these cases look like. So we would need many hours to learn all the details of this, but you can just simply read all this information from the books from ABB or Danfoss or other companies who made these guides for dimensioning systems. That's why I'm not just showing the copy of those books, because I hope you will read them. So anyway, I have another example here, example number 2. This is concept torque application, and the application itself is the extruder, which you can see on the picture here. And this extruder has a speed range 300 to 1200 RPM, and the power is given for the highest speed, 1200, and the same network as in the previous example. And now we can use the same chart, and you see we have again this generic curve, generic system curve, this one, and the two alternatives are the alternatives for two different motors with two different pole numbers, 4 poles and 6 poles. So 4-pole motor will be here, and a 6-pole motor will be there. So again, we remember our range from 300 RPM up to 1200. You see, this my red line is now corresponding to this black line here. And for the second alternative, 6-pole motor, it will be the same 300 RPM. Will start here and go up to 1200. So here it is. So you see the same as this one. And in this case, the two variants are quite close in terms of like being close to the loadability of the generic curve. So it's a little bit closer competition here. So again, I'm calling you to read the ABB guide on details of this case. So thank you for watching this video, and I'm inviting you to continue watching the next one. Thank you.